Okay, we should be live. If you haven't checked biocurious.com, please do so. We're currently actually using this music from hand gesture. I'm actually using it because well, it's good for exercising, but also I'm always touching my face and stuff during when talking, so it will actually be a reminder. Well, when I do it, when I edit the videos later, I can remove those bits. So I probably won't stop doing it. It won't do magic, but yeah, it's a good reminder. Yeah, that's what thinking pause looks like. But yes, we can start a stream by generating some music as well. So it will do short notes, long notes, and it has a scale. And that was a false detection of the other hand, which has a different scale, which is more annoying. That's why I don't normally use it. I'm left-handed, so I probably should switch between them. And only after finishing this, after publishing this tool, I realized I'd never heard of the theremin before. But yeah, it's a really cool instrument. But that one has a distance to an antenna, and then another antenna that controls the volume. So I probably should have done it that way, but yeah, maybe next time when we get to it. And yeah, if you haven't checked any of the other tools, please do so. Currently, we're working on fuzzy logic. We'll start the development in a second. We might as well start now. So we're combining fuzzy logic with this ECG game. So it's essentially a bot that will be playing the game for us, or in addition, so we could like compete with the robot. Currently it looks like this. Might restart. It has now a noise option. That's mainly to see how well the robot is doing when the noise is increased. So currently it's just generating all these false alarms. We will be fixing this before publishing the tool. And yes, you can still play yourself by clicking on abnormal ECG. The text to speech can never get me saying abnormal. It always thinks it's something else. So you should not click on that one, which was a normal ECG, and this one missing a bit, missing the peak and at the front. So we are not clicking on it. We're getting correct rejection. And when clicking on an abnormal ECG waveform, we get a hit. And that's what the bot does as well. We had a tuning of it before that just works 100% of the time, but it was relying on some magic numbers that we now removed. The system now performing much worse. It's essentially clicking on everything. It's making a decision that everything is abnormal, and we will be fixing that. We're looking at was it 4 parameters: positive peaks, the number of positive peaks, the number of negative peaks, amplitude, and the R peak sharpness. So it's assuming that yeah, so this is when I have to go edit this stuff in the video when I'm doing something funny with my face. So obviously now I can win the bot, but we pretty sure can easily make it work much better, to the point where human can sit back, relax, and watch the robot in action. And so we have these 4 files, obviously this HTML that you see on the screen. might start populating GPT. We might try and do something different. We also get, before you're screaming at me, I also do use a GitHub Copilot, but it's most of the time not producing great results. But yes, we use that as well. So we have HTML. Something funny with how the text box on the OpenAI website works. I don't know, it could be specific to Chrome on Linux. Then we have, so the waveforms are being generated using simple math equations. This is all happening in JavaScript, so front end, and the fuzzy logic, which I'll get to in a sec, is working back end. So the fuzzy logic, the robot doesn't know what the current waveform label is. That's so. Before you start saying, when playing against the robot, before you start saying, oh, the robot is cheating somehow, no, it doesn't have the labels. Now we have this game logic, doesn't do much. We might as well get the Copilot to work just by explaining the code quickly. And we'll try this one shot prompt, single shot, because it tends to work better to begin with, and then performance drops with consecutive prompts. Yeah, we do constants, waveform functions, variations. Yeah, we have a bunch of variations, as you can see, as you saw in the game itself. Generation and noise addition is also in JavaScript. And now the big reveal, the Python code. So this one has it's a Flask application, and it does the fuzzy logic business. So paste it as well. The game logic, I don't think it does much, but we will explain it with Copilot as well. It actually does quite a bit initialization, drawing the game itself, so it does the scoring in the game, calculating the scores. Yeah, I probably should break it up a bit, but it's yeah, 200 lines of code. It's not too bad. It does the waveform analysis, noise level adjustment, and starting the game. Now the Python code. This message is too long. Okay, so the Python code, yes, it's 400 lines of code. Could get rid of GitHub, what's called the ChatGPT can take how long a message can be. It's taking the code as an input. Yeah, it won't tell you, because it won't reveal any information about itself, but oops, yeah, that's the kind of stuff we have to then edit out in the video. this thinking pause. Yeah, the pod currently as it is, it just keeps saying that everything is abnormal. You can still get some points out of it. Well, because the algorithm generation, I think, is biased. I think it has something around the other thing with Copilot, the good thing about it is we can use this workspace and actually ask what's the ratio between normal and abnormal ECG waveforms. So it will try and find the relevant bit, supposedly in all the files that are currently open. It should tell you the reference as well, so it should tell you what it was looking at. But yeah, it's taking some time. So it looked at the waveforms.js and the HTML file, and it didn't produce a result, which is unfortunate because I think it's 60/40. I can check. It was looking at the wrong file. I vaguely remember something about the 60/40, but I can't confirm. Where's the generate waveform noise level? Yeah, this one, 0.6. Yeah, so it is 60/40. Well, that's why by clicking on every waveform, you are able to overall, over longer periods of time, gain some points, but you won't be doing very well because you're producing all these false alarms. So yes, there's the 52/38 ratio. So yeah, this is the kind of stuff Copilot is not being able to handle, even though it's fairly simple stuff. Okay, so we are live streaming online. Well, actually live streaming on 3 different platforms, so we won't mention the names. We are developing this Flask application that we would like to publish today, but I need your help. We need to update the fuzzy logic algorithm parameters, as in the rules and the membership functions. We also got some examples of the output that I'm getting. Can you look at the fuzzy logic analysis result? And obviously we also having an issue with the number of peaks being calculated. I assume this is to do with the noise. Last time we were trying to add a basic filter, but if we do that, we'll have to show it to the human playing the game as well to keep things fair. Can you suggest the specific code changes or prompts for GitHub Copilot? So if you could generate code with placeholders that GitHub Copilot could fill out, that would be great. Please go over all of the code provided and the images uploaded. Yep.
You've got a comprehensive Flask app with embedded JavaScript for waveform analysis and game mechanics, plus a fuzzy logic analysis in Python. Let's break down what you're looking for. Fuzzy logic algorithm parameters. Your fuzzy logic setup needs refining. You want rules and membership functions that accurately reflect the characteristics of the ECG waveforms and their abnormalities. Output analysis. You've observed some inconsistencies in the peak calculations, likely affected by noise. Filtering and fairness. You considered applying a basic filter to clean the noise, but want to maintain fairness for the game participants. Given the complexity of the ECG signal, especially on the noise, the fuzzy logic rules should be sophisticated enough to differentiate between nuanced patterns. Here's a game plan. Refine fuzzy rules. Ensure that your rules account for normal variations in ECG waveforms so that only genuine abnormalities increase the abnormal score. You'll want to look at aspects like the typical number of peaks in a normal ECG cycle, expected variations in amplitude due to noise versus pathological changes. Adjust the prominence and height parameters used in Skippy signal. Find underscore peaks to be more tolerant of noise. Implement a pre-processing step to smooth the signal, such as a moving average or low pass filter, which can help reduce the effect of high frequency noise. Fairness in filtering. If you apply a filter to the signal that the fuzzy logic sees, you should apply the same filtering in real time to the waveform displayed to the user. This way, both the human and the algorithm are making decisions based on the same input data. For the fuzzy logic part, you need a balance of specificity and sensitivity. You don't want to tag normal variations as abnormal, false positives, nor do you want to miss actual abnormalities, false negatives. Adjust your membership functions to reflect the degree of certainty you have about a segment's abnormality based on the input variables. Here's a sample set of refined fuzzy rules and membership functions as placeholders that you might want to consider for GitHub Copilot to fill.
Right, so
these are starting points, and you need to iteratively adjust these based on the performance of your system in detecting the ECG abnormalities. For the peak detection issue, here's a possible direction. Remember to integrate any pre-processing step into both the analysis pipeline and the real-time display for the user. Lastly, since this is an iterative process, you want to test these changes extensively and tweak them based on the results you're getting. This isn't a one-size-fits-all kind of situation, and
yeah, GPT-4. Yes, single shot prompt. I mean, it's everything seems legit. However, the code is not quite there. So it's suggested just to rename the sharpness. That should be fine. We don't have to do it. Oh, it's actually changed it from triangular to trapezoidal with a triangle in the middle. We already have this code. I'm not sure why it's generating it again. I don't think this will make much difference, so comment that out. Put in a comment that was a GPT-4 suggestion and not tested. That's fine. It's doing the same for amplitude. And yes, using trapezoidal membership functions instead of triangular ones, which yeah, I don't think it will make much difference. I used trapezoidal ones before. They kind of make more sense, but the triangle ones should work just fine. Yeah, I'm not sure why they decided to make these suggestions. I think it's saying Copilot can do the rest kind of thing. Right, now the rules. The rules is something we do have to go over. Now, yeah, when noise is removed, so that's actually what we are trying to show, is that when there's no noise, the algorithm, the machine, the fuzzy logic algorithm is doing much better. So it's labeling this as abnormal, which is correct. Yeah, it's now started moving much slower because the human went a negative score. Well, that's because I wasn't paying attention. It's a normal ECG, so I should get 10 points. Yeah, I'll need 12 correct responses to get back to 0. The machine is doing okay-ish. So that's after lowering the noise level all the way to 0. So the false alarms and misses are at 57 and 21. Ideally, it will just stay that way. Yeah, so with no noise, the fuzzy logic is doing pretty good. I think it might not be making any mistakes whatsoever. So for the demo, we might just add the low amount of noise where it does mistakes sometimes. No, I just did a miss. So there was an abnormal waveform and it didn't click on it. So it's making mistakes even when there is no noise. This is something we definitely want to sort out. It should be pretty straightforward. There's some sort of basic adjustments that we need to make. The positive peaks 3 and 1, these are working okay. The amplitude doesn't look like raw amplitude. That amplitude doesn't seem to be changing at all. It's always 0.83y. Now it changed to 0.5. Right, when you don't have the negative peak, the amplitude is changing. 0.58 seems to be the maximum amplitude, which is a bit odd. It should go to 1 or as close to 1 as possible. Yeah, so that the amplitude is probably not, oops, it's the false detection of a hand. Yeah, it's sometimes falsely detecting a hand on my ear or something like that. The music bit. I don't know if you call it music or not. I do. When the false alarm stayed at 57, the misses went from 21 to 28. So I think it's missing a very specific waveform. The thing about it is that we don't want to tune it up. We don't have any, we don't want any magic numbers that make the algorithm work better. We want to just give it the general instructions and for it to just do its thing. Let's go over those suggested rules. Might need to explain each one. Because I forgot what they do. Don't fit the screen as well, which is not good. Yes, those are again GPT-4 suggestion. Don't think we will be testing this because that's not what the problem is. Right, the peak detection. It's suggesting to change the prominence value. And yes, we do have a prominence value. Currently, yeah, every time you do something funny on your face, it's a prompt for me to have a break and listen to some music. Hopefully this music is not copyrighted, Assuming if you create a musical instrument, then the music is yours. I don't know. What do you think? Just a quick recap. We tried this single, what's called one-shot prompt of GPT-4. To try and fix some things with this fuzzy logic algorithm that is playing this ECG scoring game. But it's currently hallucinating a bit. I'm pretty sure one of the waveforms that never detects correctly. That's why the misses. So it's always missing one abnormal ECG. And yes, I know which one it is. So this is kind of unfair for me to do this because I know exactly what the waveforms are. Later, at a later stage, we also try to add. We can, because there's synthetic ECG, we can add like an infinite number of different waveforms and see how the algorithm responds. So the rules should just be logical, nothing fancy. So when we get the error in GPT-4, was an error generating a response. Obviously, if I click regenerate, it will start again. It was a long prompt and a long response. What if I just refresh the page and haven't finished? When it's in this continue generating position, it actually gives me an option to interact with it again. So I don't have to continue. If I do continue, I suspect it will give me the same error again. Yes, that's right. So it's behaving in an odd way. I don't know, is it just for me? Is it because I'm using the Chrome browser in Linux? I was thinking actually doing a tool where it's using an API and my Python just prompts the GPT for whichever model just continuously non-stop. Obviously monitoring the cost. Maybe it will be even cheaper. I mean, you can always cap it at whatever $20 a month that the GPT-4 cost. Sorry for that, that's how drinking sounds like. This is the other hand. I like the other hand much better. I was saying I have to change the hands because I can do both at the same time. That was the idea, but that's essentially like playing two musical instruments at the same time. I wonder if there's any musicians in the crowd who would like to test this and provide the feedback. Okay, I don't know, GPT-4 just got stuck on me. Yeah, there's no point asking you anything about the behind the scenes of how this terminal actually works, is there? So I think we will just have to leave with it. So you generated pretty generic responses. I'm trying to get to the specifics of the code. Now it seems at the moment, in the past we removed the frequency metric. We were looking at the frequency as a parameter, and now the result of it is that we always get a miss for a certain type of waveforms, synthetic waveforms, that have the R peak too close to the T wave. This must be because we removed the frequency component. How would you suggest fixing it? I would like a specific code. Yeah, I'm thinking, should we bring the frequency back? The reason we removed frequency to begin with is because we are not looking at the continuous ECG waveform. We're looking at each QRS complex one at a time. So it kind of didn't make sense to look at frequency. But obviously now it seems like that might have been a mistake, because if the R peak is moving around, being too coming too quickly or coming too late, we don't have a detection mechanism for that. We could, of course, look at distances between peaks, but then we'll have to make an assumptions as to which peak is which. And also, if we have a missing peak, that would not work as well. Any suggestions are welcome. Yep.
It sounds like the removal of the frequency metric from your fuzzy logic analysis has created a gap in your ability to accurately characterize ECG waveforms where the R peak is too close to the T wave. This is indeed a crucial aspect of ECG waveform analysis, as the timing between different peaks, like the R interval, for example, can indicate various cardiac conditions. If the frequency component was helping in detecting such abnormalities, one approach would be to reintroduce a similar metric that considers the timing between peaks. Since you're looking at QRS complexes individually, the concept of frequency might not apply directly, but the interval between peaks is still very relevant. Here's a high-level suggestion for your Python code that involves calculating the interval between peaks and using that as a metric. Calculate intervals between peaks. For each waveform, calculate the intervals between the significant peaks, P, Q, R, S, and T. For example, measure the PR interval, QRS duration, and quart interval. Create a fuzzy variable for intervals. Define a new fuzzy variable for each of these intervals with appropriate membership functions based on normal ranges. Define rules using intervals. Create rules that consider these intervals. For instance, a short quart interval might lead to a higher abnormality score. Here's a conceptual Python snippet to get you started.
It's nice, but again, what happens if one of the peaks is missing, as we do, well, have happening in reality, and specifically in reality, one of the peaks might be missing. So how do we deal with that? When calculating intervals. How would you make an assumption which peak is which? and which one is missing.
In the code, PR_interval, QRS_duration, and quart_interval are placeholders for the intervals you calculate. You'll define ranges and membership functions for these based on the typical values you expect in a normal ECG. Then, use these as antecedents in your fuzzy logic rules. Adjusting your peak detection to be tolerant of noise will still be important, but this approach gives you a way to capture the temporal relationships between peaks that are crucial for diagnosing certain cardiac issues. By doing this, you bring back a form of frequency analysis that's tailored to the segmented nature of your ECG analysis, which could mitigate the issue of missing certain waveform abnormalities. This method also naturally extends to handling missing peaks, since the absence of a peak would drastically alter the expected interval, thus flagging a potential abnormality.
I wasn't actually listening to the pod, but yes, it's suggesting to add these 4 intervals. That yes, it's we have similar stuff obviously in the waveform generation. So say we have these 2 QRS variations. So one of them will have a gap between, so the R peak comes late. However, the fuzzy logic algorithm, the bot, the machine that is playing the game, should not know about how the waveforms were generated. So are you suggesting adding 3 more parameters? I don't think this will work because again, some of the waveforms might be missing some of the peaks. Not might, they are missing some of the peaks. How do I say peaks correctly? Yeah, I don't want to trigger the microphone. That's why I'm trying to say the P in a softer way, but the speech to text never picks it up correctly. Peaks. Peaks. Yay, English is funny that way. Funny. Yep. Oops. Really have to get rid of those false detections of the other hand. It's really annoying. I think it might be happening when it's over the face. When the hand is over the face. Don't really need the face detection, might get rid of it. Clear.
The challenge of identifying which peaks are present and which are missing is a common one in ECG analysis, especially when dealing with noisy data or atypical waveforms. In a real ECG, missing peaks can indicate a variety of cardiac arrhythmias or abnormalities, so it's crucial to handle this correctly. Here's a step-by-step approach to deal with missing peaks in an algorithmic way. Peak detection robustness. Use a robust peak detection algorithm that can handle noise and atypical waveforms. You can employ methods like adaptive thresholding or machine learning-based peak detection. Peak labeling. After detecting all the peaks, you need to label them. You can do this by looking at the expected sequence of peaks, P, Q, R, S, T, and the typical relative positions and amplitudes. For example, the R peak is usually the highest positive peak, and the S peak follows the R peak. If a peak is missing, like the P wave, the sequence will be disrupted, and you might see a different pattern. Assigning intervals. Once you have labeled the peaks, you can assign intervals. If a peak is missing, you can skip the calculation that involves the missing peak or use a placeholder value that indicates a missing peak. Fuzzy logic adaptation. Adapt your fuzzy logic system to handle missing data. For instance, if the PR interval is missing because the P peak wasn't detected, your system should increase the likelihood of an abnormality. Account for variability. Understand that in the real world, the distance between peaks can vary even within the same patient over time. Your algorithm needs to account for this variability and not rely on fixed thresholds. For the fuzzy logic part, here's a sample of how you might modify your code to handle missing peaks.
Yeah, I'll have to read this again. So yeah, humans are really good at getting distracted, aren't they?
In the above code, we use none to indicate a missing peak and adjust our fuzzy logic inputs accordingly. You may decide to input a specific value that indicates a missing peak to the fuzzy system, or you can have separate rules that specifically handle missing data scenarios. Finally, about your speech-to-text issue with the word peaks, it can indeed be a bit tricky. If your speech-to-text software is consistently misinterpreting it, you might need to enunciate very clearly or even consider using different software or adding custom words to its dictionary if that's an option. But in the context of coding and development, as long as the term is clear in the written code and documentation.
Getting this network errors with GPT-4. Copilot also playing up, saying it doesn't have the code, which is a bit odd. Yeah, GPT-4 didn't finish the code. We need to regenerate the whole thing. When we regenerate, there is normally an option to move back and forth to the new and the previous version being generated. Yeah, monitoring altitude at the moment. Yeah, we really need to fix. I didn't remember that we have a calculate membership as a separate function, but that's only. Now that doesn't do much. So we actually need to select a code. Okay, now it's working. Yeah, so we're implementing a fuzzy logic system to analyze some data. Yeah, it doesn't know what data we are looking at, even though could have looked at the names likely related to ECG readings. Okay, it did do that. You have to actually read the whole thing, don't you? Fuzzy logic is the form of many valued logic in which the truth values of variables may be any real number between 0 and 1. Yeah, so all the numbers have to be normalized, which is I don't think that's the case at the moment. Well, especially not when we have noise, then the number of positive peaks just shoots up through the roof. Yeah, when we remove the noise, it just gives the correct number of positive and negative peaks. Might first sort out the no noise situation. That will kind of make sense. Yeah, I think it's still giving. We had a frequency component. Sorry, I keep repeating the same thing over and over again, but that's important. That's why our system is not working at the moment. It suggests that looking at calculating intervals. The thing is, Python code is already 400 lines of code, so I'm not sure if we should add the extra parameters or not. I think it's suggesting 3 parameters. If we are calculating the QRS detection, do we still need the R peak sharpness to be calculated? Might have more questions as well. Yeah, so the intervals are nice. Then we asked what happens if one of the peaks is missing. And I was suggesting to calculate intervals with missing data, an additional function. Obviously, every time you ask for something, it generates an additional function. So can I make sure I understand what you mean? If I have do I still need no, but by looking at the inputs of these functions, the answer would be yes, that I do still need them both. It just inflates my code. So after the suggested changes, how many parameters and what are they we will be looking at? Yep.
Calculating the QRS duration and the sharpness of the R peak can serve different purposes and give different insights into the waveform. QRS duration. This metric gives you information about the overall width of the QRS complex, which is valuable for identifying certain types of cardiac abnormalities, such as bundle branch blocks. R peak sharpness. This measure can indicate the steepness of the R wave's ascent and descent. It's useful for detecting specific conditions that affect the shape of the R wave, such as myocardial infarction or pericarditis. So, even if you're calculating QRS duration, you might still want to calculate R peak sharpness because it provides additional, complementary information. Now, regarding the functions you mentioned. Def calculate _intervals_ with _missing_ data, detected _peaks. This function is intended to handle situations where you may have missing peaks within your ECG waveform. It uses the detected peaks and calculates the intervals between them, even if some are missing. Def calculate _intervals, waveform. This function seems to calculate intervals based on a complete waveform with no missing peaks. If you have two separate functions for calculating intervals, one that assumes a complete waveform and another that can handle missing peaks, you may end up with redundant code. Instead, you could combine these into a single, more robust function that calculates intervals and handles missing data within the same function. Here's an example of how you could do that. With this approach, you have a single function that calculates all the necessary intervals and the R-peak sharpness, handling missing peaks as part of its logic. After these suggested changes, the parameters you will be looking at are the intervals between identifiable peaks, which may include the PR interval, QRS duration, quart interval, etc., and the sharpness of the R-peak. You may have a different number of parameters based on what is detectable in the waveform. The goal is to streamline your code to avoid redundancy while still capturing all the necessary information from the ECG waveform to make accurate determinations about cardiac health.
So we're adding another function. Assuming waveform is NumPy array, calculate the intervals between peaks. For example, the intervals between R peak in the ECG. No, we do not have intervals between R peak because we're looking at individual BQRST. No, so that's no good. Has the peak detection logic. Do have that function. Why do you stuff up the name? Yeah, we have peaks mentioned 174 times. Just the variable, is it? Yeah, we just have them in processed data. Can we have it in a separate function? Yeah. There's a placeholder. This is not being should be def. Can Copilot do anything useful? Let's do a musical break. Check for any questions as well. I don't think there are any, but we will check anyway.
With this approach, you have a single function that calculates all the necessary intervals and ER peak sharpness, handling missing peaks as part of its logic. After these suggested changes, the parameters you will be looking at are the intervals between identifiable peaks, which may include the PR interval, QRS duration, quarter interval, etc., and the sharpness of the R peak. You may have a different number of parameters based on what is detectable in the waveform. The goal is to streamline your code to avoid redundancy while still capturing all the necessary information from the ECG waveform to make accurate determinations about cardiac health.
Can you generate the following functions? Or regenerate them if you already generated them before? Can you make sure you include all the necessary code in the function so it can be executed with no errors? We eventually want to integrate everything into app by yep. What's it analyzing for? Yeah, don't like when always expand the output, okay. Don't like when it's analyzing, it means it's trying to execute something on its own server, I think, which is not what I want. I need the code in text form. Yeah, because now it will say, oh, I can't execute it, I don't have the data. Something silly like that. So I'm not sure why try to begin with.
I have created placeholder functions for detect_peaks and calculate_intervals in Python. You would need to integrate and adjust them based on your actual waveform data. The detect_peaks function is designed to detect peaks using the skippy signal find_peaks function. I've set a relative height threshold of 50% of the maximum value of the waveform and a minimum distance of 25 samples between peaks. These values are arbitrary and should be adjusted based on the characteristics of your ECG data. The calculate_intervals function uses the indices of the detected peaks to calculate the intervals between successive peaks and returns these intervals in a dictionary. Again, you might need to modify this function to fit the specific peaks you're looking for, e.g., PQ, QRS duration, etc. Here's the code for you to integrate into your app.py.
I think it's looking at my previous code. We shared all the code with you. So first, I don't think it's a good idea to try and execute anything on your server. Give me the text of the code.
To integrate this into app.py, you would place these functions in your script and call calculate_intervals within your process_data function. Make sure to replace your _waveform_data_here with your actual data when using these functions. Please note that this code is a starting.
It kind of always fails at the end of the response, which is a bit odd. It's actually not bad. The minimum number of samples between it's meant to be consecutive, successive peaks. Well, one thing is for sure, GitHub. ChatGPT is much better, has a much better English than I am, that's for sure. But yes, I like that one, turning peaks. So it's a different way of calculating peaks. Calculating intervals. Does this have a missing? Before we had a missing bit. Still calculating the RP sharpness, that's okay. Usage is good because later when we update the code above, it might just refer to this, hopefully. To refresh this page. How about the missing? That one was dealing with missing data. Okay, this is messy. Why is it returning? the new one is not dealing with missing peaks. By the way, just a reminder, all the tools we make are available on bionichaos.com. Go check them out. And don't forget to leave your comments. That can be on any platform, wherever you watch this. The website doesn't actually have a tool for it. Yeah, the other thing is we are gonna be doing a summary of all available biomedical datasets. There's quite a lot. Yeah, the good thing about GPT-4 now actually providing links. I'm more familiar with the EEG ones. So it gave actually not know any of those to know if they're legit or not. It does provide the links now from where it actually took the information. So this is from a README file from 6 months ago. Looks like quite a comprehensive list of EEG datasets. Yeah, IEG.org is not on the list, I think. Kind of really comfortable showing what's on GitHub because of, where is it? The license. Where's the license? Well, anyway, it all meant to be open source, Creative Commons or MIT, one of those permissive licenses. And you have a page here. Yeah, so this is on publicly available EEG datasets on OpenBCI website. Yeah, I don't want to show that, not because I don't like it, but because there might be some copyright issues, even, you know, by showing the logo. This one is an open Discover EEG and open fully automated EEG pipeline. I mean, I'm not sure what they use the word pipeline, might suggest it's not actually accessible. Frontiers, so this push should be open source website as well. But yeah, so in this case we have this NMT, this name comes up a lot. Scalp EEG dataset, open source annotated dataset of healthy and pathological EEG recordings for predictive modeling. Now that's all nice and good. There's a standard montage, so that's nice. Some histograms on the population, age, and abnormal, normal EEG. Dataset structure, that looks all great. But obviously, one will be looking for the link to the actual data, which must be hiding somewhere at the bottom of the article. There it is. When you open it, it sends you to this weird university website that has some dataset code repository download. Yeah, that's obviously not related. Here it is, halfway through the list. I have code sitting on GitHub, and then you have this zip file sitting on this chatbotmart.com, and when you open this one, it goes to GoDaddy. You can buy chatbotmart.com for I don't know how much, and obviously the data is not available. So that's zip file. You know, when linking from the paper is nowhere to be found. We of course can try the GitHub. This also has link to the dataset. It's from 2 years ago. Data folder, labels, good. Doesn't seem to have the actual data. Right, this one now has a different link, which goes to the same thing. The Chatbot Smart. Are all of them on Chatbot Smart? No. Anyway, the links are just weird. Yeah, from all over the shop. So I'm not sure if this dataset is available anywhere. So yeah, that's what happens to most of public datasets. So this lists here. And educated guess that only like 1% or so, under 10% of these datasets will actually be available. Some will require some sort of crazy registration, and some just essentially not be available anymore. But yes, we will be essentially creating a list like that and indicating, you know, essentially some sort of difficulty score of how easy it was or how difficult it was to actually get hold of the data. And once you do get hold of the data, the main question then is if the data is in its raw format or some sort of metadata, like downsampled or processed or whatever, which we do not like. Okay, a couple of things with the code that we currently have. We need to fix it and integrate it properly. Can you help with that? Ideally, just regenerate the whole code. If it's too much, regenerate functions. If that's too much, give instructions for GitHub Copilot to do it. We want to make sure that with noise level set to 0, the fuzzy logic algorithm doesn't make any mistakes. I think for that we need to sort out that frequency component for which sorry for that noise. So for which we have, I think instead of frequency we now have the distance, the time between the different peaks, but it's not currently being fully integrated. We need to add the membership functions for it and the rules for the additional parameters. Can you do it yourself or provide prompts for GitHub Copilot, whichever way you prefer? By the way, if you feel like being funny or something, go for it, but probably not too funny. Something really wrong with the text window, with the window we insert the prompt. Yep. I would expect it to scroll automatically to the bottom or something, but it doesn't do that. Clear.
Understood. You're looking for an integrated solution that correctly processes ECG waveform data with noise level set to 0 and makes use of the intervals between peaks in the fuzzy logic analysis. Since the frequency component has been removed, the intervals between peaks will serve as the new metric for analysis. We will need to modify detect_peaks to handle noiseless data accurately. Integrate interval calculation into the processing function. Add new membership functions and rules for interval-based analysis in the fuzzy logic system. Here's how you can integrate everything into your Flask application, along with placeholder membership functions and rules that you can further refine.
Still generating. Might take a while. Yeah, I mean, we have been working on this tool for quite some time. Yeah, that's the one that's always being missed. So that's the one we always get the miss for currently. How many rules?
In this code, you need to add the logic for calculating the specific intervals you're interested in. For instance, the RR interval is the time between two consecutive R peaks, and you might want to add PR interval, QRS duration, and so forth. Ensure to populate the intervals dictionary with the calculated intervals and use them as inputs to the fuzzy logic system. Update the membership functions and rules to match the actual intervals found in normal ECG readings. Remember, this is a template and requires testing and refinement to ensure that it functions correctly with your specific ECG data. Regarding the noise level set to 0 requirement, you would ensure that your waveform data is noise-free before it's processed by this system. If you have any noise reduction or filtering implemented, you can skip it or set the parameters to a state that doesn't alter the signal. Lastly, to avoid any text window issues, make sure your IDE or text editor is functioning correctly, and if the issue persists, consider resetting it or switching to another editor. If you're using a web interface for coding, check for any browser extensions that might interfere with the text input.
Yeah, we're not plotting anything in Python, so we can comment the matplotlib pyplot out. Yeah, everything else is correct. Yes, we have this Flask application. Have the analyze waveform. We have data processing. Let's save a copy of this quickly. Git is not properly working. Because I mean, eventually I don't mind for the whole project to be on GitHub, but just gonna be an absolute mess. So essentially what you see on the website is trying to deal with that mess. There's a lot of tools that actually not being listed that are under development. You can go to them if you know the URL. Like the bot currently, this one would not be working because we haven't added it as a Flask application yet. So we don't do frequency anymore. So in processing the data, we should calculate intervals as well. After existing peak detection, yeah, we have it for debugging at the moment, the plotting is stuff that I don't think it will actually work at the moment. Or maybe it will. We have to bring that plot function back. Yeah, so this is how the current detection works. So just keep overlaying stuff. This is the type of waveforms that we have. Yeah, so this noise level is found 35 positive peaks, which is obviously not correct. Okay, this will keep popping up. Will be an easy way of breaking a stream and everything. Okay, so finding the peaks and doing the amplitude calculation, printing it out as well. We are not normalizing it because this is essentially dividing by 600 will do the normalization. Yeah, we're not returning processed data. Are we doing it for any other parameters? No. If you're doing extra hours. Yeah, that's plot. It's trying to plot still. That's okay now. Yes, we're running this application only locally at the moment. Yeah, we better not do this again because it's plotting stuff in the backend. It breaks the flow of the software. Yeah, it's okay to print the intervals. So need to add them in here. Where does it get the frequency from? It should be intervals. Yeah, data is for whatever reason being generated at the DC level of 300. So we actually reduce it back to 0. That's instead of detrending. Yes, we could use a fancy detrending algorithm as well. Do we have frequency currently? Yeah, the amplitude is not normalized anymore. Can get rid of that. Don't have frequency. Abnormality is now called abnormality score, and we also produce a decision. So it's a yes, no, normal, abnormal. A decision. Yeah, I wasn't sure about this auto generation of membership functions. I don't think we need this. Where's yeah, process data. We have the intervals, and the intervals should be returned. Oops. Yes, intervals. That's right. Yeah, don't need that line. Let's do some music and recap. Have the calculate intervals function. Why is it giving a different function every time? So this is better. This is covering a case where there is no R peak, for example. Now we need to modify, get rid of that. Yeah, and fuzzy logic analysis. That's the tricky business. Yes, so we don't have RR interval because it's not continuous waveform. Can we rewrite this function taking into account the newly added parameters that are to do with the time distance interval between the different peaks? Yep.
To rewrite the fuzzy _logic _analysis function with the newly added interval parameters, you'll first need to define fuzzy variables for each interval you're analyzing. You'll also need to define membership functions and rules for these intervals. Here's how you can adjust your fuzzy _logic _analysis function. In the rewritten function, I've added a new antecedent for the RR interval, defined its membership functions, and created new rules that relate the RR interval to the likelihood of abnormality. This is just an example, and you need to adjust the ranges and membership function parameters according to the specifics of your data and the expert knowledge you have on ECG interpretation. You would also add similar antecedents, membership functions, and rules for any other intervals you're analyzing, PR interval, QRS duration, etc. Remember to test the new fuzzy logic system thoroughly with a variety of input data to ensure that it's functioning as expected and making accurate assessments.
Getting confused here. Again, just to make sure we are clear, we are reviewing every individual PQRST waveform at a time. So doing an RR interval would not make any sense. Instead, we would like to be able to detect if the R peak is too close to the P wave or the T wave within the one complex. Yep.
Thank you for clarifying. If we are analyzing individual PQRS complexes and need to determine the proximity of the R peak to the P wave and T wave within a single complex, we would focus on the PR interval and the RT interval respectively. These intervals are important in diagnosing various cardiac conditions. Here's how you can adjust the fuzzy_logic_analysis function to include these considerations.
Can you continue the code generation and address a couple of questions? Why the RT and PR intervals antecedent variables do not go all the way to 1 but 0.21 instead? Also, with the rules, instead of adding 4 new rules, is there a way combining them all, considering the output for all of them for the abnormality is set to be likely? Yep.
Certainly, let's continue the code and address your questions. The PR and RT intervals are typically measured in tenths of a second, hence the 0.21 upper limit, which could represent 210 milliseconds. However, the actual range will depend on the typical duration of these intervals in a normal ECG. If you expect intervals to be up to 1 second, then the range should indeed go up to 1.0. The choice of 0.21 was arbitrary and based on a common duration for PR intervals. It should be adjusted to reflect the actual data you are working with. As for combining the rules, since they all suggest the same outcome, likely, abnormal, you could create a composite rule that triggers when any of the conditions for the PR or RT intervals being too short or too long are met. This would simplify the rule base. Here's how you can continue the function and implement these adjustments. This code snippet completes the fuzzy_logic_analysis function and incorporates the modifications for the PR and RT intervals, as well as the combined rule for an abnormality. Ensure that the rest of the function, as well as Rule 1 through Rule 6, are implemented appropriately with your data. Remember, this code needs to be tested with actual ECG data to fine-tune the membership functions and rules to match clinical standards and ensure accurate analysis.
shared both the current Python code that we have and the game logic JavaScript as well. Probably the JavaScript needs some adjustment considering we added more parameters to the mix. Can you review the whole code and explain why potentially we're getting this error?
The error message you're encountering, error in analyze_waveform, PR_interval, indicates that when the fuzzy_logic_analysis function is called, it expects an input for PR_interval, which is not being provided. This is because the process_data function calculates the intervals, but does not separate them into PR_interval and RT_interval, which are required by the fuzzy logic system you've set up. Here is a step-by-step review to address the issue. Ensure that process_data actually calculates and returns PR_interval and RT_interval. Add these intervals to the processed_data_converted dictionary before passing it to fuzzy_logic_analysis. Update the fuzzy_logic_analysis function to use these new intervals as inputs to the fuzzy system. For the JavaScript part, you'll need to update the function display analysis result to include elements in your HTML to display the new PR_interval and RT_interval if they are part of the response data. If they are not meant to be displayed, but are used for calculations, ensure that the server response includes these values, and they are passed correctly within the analyze waveform function. Here's how you might adjust the Python code for the fuzzy logic to handle these intervals. Remember to adjust the actual calculation of PR_interval and RT_interval according to your data and how these intervals are defined in the context of your application. The above code assumes that you have already calculated these values and added them to the processed_data dictionary. If you haven't, you need to implement that calculation based on the detected peaks in the CoffEEG waveform data.
Yeah, we're getting a bit confused now. Yeah, the more prompts we're doing, the less bang for the buck we are getting. There's something wrong now. Can we actually get the GitHub Copilot to do this instead? Might use the workspace function because we don't actually know where do we need to make the change. Essentially, we added more parameters more features to look at. Right, so in process data, sometimes it provides these links that are very helpful, so that I don't have to search for the code. So we're calculating the intervals here somewhere. Yes, and we were not doing this correctly. This is still not correct, but this is better. Yeah, get rid of the print statement. We will display it on the front page eventually, so we'll need to change the HTML code as well. I'll share it with you in a second. It should be just called NP data. And we don't need that. Can we just update? When it's updating, it should be looking at the previous code or any changes we made. No, it's not doing that. As well get rid of it. Oops. Oh, come on. Print interval. PR interval. Yes, that's what we want. Then RT interval. So this is correct, and we returning all that. So that's fine. So in calculate intervals, it's not a hypothetical function, it's an actual function. Clear. Clear. Doesn't want to clear. So we're adding them to the dictionary before passing on. Let's do the same thing again with a workspace function. Update the fuzzy logic analysis function to use these new intervals as inputs to the fuzzy system. Let's see if it can find the relevant code. We'll give GPT-4 a bit of a break just so we also don't hit the 40 messages per 3-hour limit. So it's still searching for stuff. We'll ask it eventually to give an overview for what we have so far. I think it's getting stuck. Can you get it to work twice? Request timeout. What? It's a weird server error. Oh, this one is not doing anything. In fuzzy logic analysis, that's where the function is. But we can do that to select the whole code. No, we cannot. We're not doing the calculation in this function. I have this funny default rule that I thought we got rid of. We're not actually. No, we are using it. So we have those 6 rules: a default rule and rule for abnormal intervals. So essentially, if they're too short or too long, the abnormality of the signal is highly likely. Let's actually test this again. We still get an error. Yeah, calculate intervals should take 1 positional argument, but 2 were given. That's not good. I think this might be something for a Copilot to sort out. And because we don't know where it is in the code, we just use the workspace function. So it tries to find it itself. I mean, yeah, GPT-4 is so much better with these things. Well, pretty much anything. Okay, calculate the intervals. We have the it's not in calculate intervals. You mean this one? No, this is just initializing an array. I want to do an oops, an interval type. If is okay. We're not using interval type. Okay, that should be fine. Now we actually need to use the interval type. Interval type is not being used. I think we need to rewrite the whole thing. Returning intervals. Yeah, now it's doing the interval between R and T wave and P and R wave instead of R, which we don't have because we're looking at each PQRST complex individually. So this should be better. Still getting an error. Might pop it into a GPT-4. Yeah, if I select the whole code, it might tell me that the code is too long. No, it's dealt with it. 500 lines. In analyze waveform. Now it's not getting the links, which is pretty annoying. So we have the analyze waveform. It actually do this for me. It's only taking one line of code. That's not good. Yeah, I need to make sure that the PR interval is in the JSON response. And it's not. And GitHub Copilot doesn't want to correct that. Right, yeah, interval should be there. RT interval should be there. That's it. Response data. This one's a bit odd. Yeah, now we're having another problem. Every time you fix something, you break something else, don't you? Yeah, I'm not entirely sure how to prompt a Copilot in terms of giving it the code. What code does it need? comparing it into converting there's something in the dictionary format. Oops. What's being returned here? Oops. Yeah, I think it's a jobby for GPT, and we will be finishing up soon, and we'll be asking it to summarize the whole thing anyway. Okay, I'll be sharing the whole code that we currently have for the Python Flask application that does the fuzzy logic analysis. We also get this error. Maybe you could quickly sort it for us. Hopefully it's nothing to do with the JavaScript. No, it shouldn't be. So I'll give the entire code, and could you also provide a summary for the whole thing and the changes that we have made today? They should be, the previous code should be still commented out in the script. If you wish to be funny or something, make general comments, suggestions. Go for it. Yep. Okay, it might be thinking for a while. Clear.
Your code shows a good approach to processing ECG waveform data and analyzing it using fuzzy logic. However, the error you're encountering seems to be related to how data is handled in the fuzzy _logic analysis function and potentially how intervals are calculated and passed. Let's break it down and provide some suggestions for improvement. Error message, less than not supported between instances of float and dig this. This error typically occurs when a comparison operation is performed between incompatible types. In your case, it might be happening in the fuzzy logic analysis where a dictionary is being compared with a float, or when processing the intervals. Ensure that the values passed to the fuzzy logic system are numerical, floats or ints, and not dictionaries or other data structures. The intervals are initialized but seem to not be populated correctly. This could be due to the logic in calculate_intervals not functioning as expected. Calculating intervals, in the calculate_intervals function, ensure that the peaks, p, r, t, are correctly identified and the interval calculation logic is correctly implemented. For instance, if you're calculating PR intervals, you need to make sure both P and R peaks are correctly identified and their indices are used to calculate intervals. When passing PR_interval and RT_interval data to fuzzy_logic_analysis, ensure these are numerical values representing the intervals. You might need to process the intervals dictionary to extract meaningful numerical data, like average interval length, maximum, minimum, etc., before passing it to the fuzzy logic analysis. In the fuzzy_logic_analysis function, ensure that the data you're inputting into the fuzzy system, like PR_interval, RT_interval, amplitude, etc., are in the correct format and range as expected by your fuzzy variable definitions. Debugging tips. Add print statements or use a debugger to check the values of intervals and other parameters before they are passed to the fuzzy logic system. This will help you identify where the mismatch or error is occurring. Improving comments and documentation. Adding more descriptive comments can help maintain clarity, especially in complex sections like the fuzzy logic analysis. This will make the code more maintainable and understandable to others or even to yourself in the future. JavaScript integration. As long as the Python backend is handling the data correctly, the JavaScript frontend should work fine. Just make sure that the frontend is prepared to handle and display any new data sent from the backend. Remember, debugging complex systems often involves checking each part of the system separately to ensure they function as intended before integrating them. This modular approach can help isolate and fix issues more efficiently.
Yeah, I'm not sure how much progress we made today. Currently, the application is not running properly. The robot is not generating any output, because we're getting a silly error. Can we summarize the whole application so far, give it a broader context? If you feel like being funny, go for it, but not too funny. Definitely do not use any emojis. No, every time I say this, it's actually picking up on the actual word and starts, it will start to actually generate emojis. Give a general context for the application, how it might be useful or not. We already have the game published on our website, but this one will obviously provide extra features where you play against the machine. Yep.
Alright, let's step back and look at the big picture of your application, with a touch of lightheartedness but not too much to throw us off course. Imagine this, you've got a game, not just any game, but one where humans and machines face off in the grand arena of ECG waveform analysis. Picture it as a, whose line is it anyway? But for ECG waveforms, where the points do matter. Players, likely healthcare professionals or enthusiasts, get to test their skills in identifying abnormalities in ECG waveforms. It's like playing a medical version of, Where's Waldo? But instead of Waldo, you're looking for sneaky little changes in those squiggly lines. Here's where your code steps in, flexing its fuzzy logic muscles. It's like having a robot judge in a talent show, but instead of judging singing, it's judging the peaks and valleys of heartbeats. The machine uses sophisticated algorithms to analyze these waveforms, considering factors like peak sharpness, interval lengths, and amplitudes. Basically, it's looking for the heartbeat's rhythm and style. Players are presented with a waveform and have to decide whether it's normal or abnormal. Each decision is a gamble, like choosing door number 1 or 2 in a game show, but with more medical credibility at stake. Meanwhile, the machine, your Python backend, does its own analysis. It's like having Sherlock Holmes, but instead of solving crimes, he's deducing heart conditions. The machine's verdict is based on fuzzy logic, which is a fancy way of saying it makes decisions in a very human-like, somewhat uncertain way. It's not just about zeros and ones, it's about, maybe this peak is too sharp, or perhaps this interval is too long. Your application is not just a simple game. It's an educational tool, a training simulator, and a way to introduce people to the complexities of ECG interpretation. It's like combining a game of chess, a medical seminar, and a detective novel all into one. You've got peak detection, interval calculations, and amplitude analysis. It's like the machine is putting on its detective hat and magnifying glass to scrutinize every heartbeat. The integration of fuzzy logic adds a layer of sophistication, like adding a plot twist to a mystery novel. The JavaScript front-end makes it interactive and engaging, because what's the point of having a cool game if it's not fun to play? Dealing with errors and making sure the data passed around is in the right format. It's like making sure all the actors in a play know their lines and cues. Your application is a bridge between gaming and medical education, turning the daunting task of ECG analysis into an interactive learning experience. It's like if Grey's Anatomy met Who Wants to Be a Millionaire? Equal parts educational, thrilling, and potentially life-saving. So, while there might be some hiccups along the way, like our current error situation, remember, every great invention had its share of tuning. Once this is all ironed out, you're not just launching a game, you're launching a new way to learn, engage, and possibly save lives. No pressure, right? Winking face.